Another one, right? Another thing to help you, just in case. LEO, loss of electrons, is oxidation. GER, gain of electrons, reduction. All right, so loss of electrons, oxidation, right? Then I know that this thing was reduced. So I'm looking for the oxidizing agent. Is the oxidizing agent oxidized, or is the oxidizing agent reduced? Reduced. The oxidizing agent is reduced. Was this one oxidized? Okay, so this one was reduced, so this one is the oxidizing agent. So A or B are our choices. All right. Who's getting reduced? Is manganese getting reduced? No. So it's B. Right? Got it? The answer is B. Because hydrogen is the oxidizing agent. This thing was oxidized. How did it get oxidized? Not my fault. Right? Somebody else did it to him, right? It's never anybody's fault. They're always a victim. See, the hydrogen oxidized the manganese. Right? So this is the oxidizing agent. Right? So what happened? Who was reduced? Did hydrogen get reduced? Yes, they did. Because manganese did it to them, right? Not their fault. Just manganese just was reducing people. It's B. The answer is B. Can you see that it changed a slight shade of, instead of black, a brownish black? The projectors is not very good. Okay. The answer is B. Anybody else want to talk about that some more? So you'll want to become proficient at this sort of thing because there's going to be questions like this. Yeah?
So mostly the oxidizing agent gets reduced?
Always. Not mostly. Always. Oxidizing agent gets reduced. Reducing agent gets oxidized. Well, you know, if I go around reducing people, right? What happens to me when I reduce somebody? So here's my electron. I'm going to reduce you. Can you catch it? I'm going to reduce you with this electron. Right? So what happened to me in terms of electrons? I lost an electron. So I must have been what? Oxidized, right? So am I the oxidizing agent? No, she was the oxidizing agent because she, here, throw me back to that pen. Play again. All right. So she says to me, what? Say your line. You don't know your line. It's, I'm going to oxidize you.
You're going to oxidize me?
No. You got to say that to me. No. I'm going to oxidize you. Do you know the lines? You try it. Say, I'm going to oxidize you. Yes. And see, she's holding out her finger. It's not a gun. This time it's a what? It's like a magnet, right? No, please don't oxidize me. Oh, she just oxidized me. So she is the what? She's the oxidizing agent. She's going around oxidizing everybody, right? And what did it do to me? Did she oxidize me? Yeah, I lost my electron. But it did what to her? Yes, I was the reducing agent. Let's play again. Somebody else this time. Ready? I'm going to be the reducing agent. Oh, never mind.
Why are you going to gun if she gets a magnet?
What's that? Say it again.
Why are you going to gun if she gets a magnet?
Well, the reducing agent has to have a magnet because if they're... No, sorry. The oxidizing agent has to pull that electron. So guns don't really pull electrons. Guns shoot electrons. I don't know. It's not a real story. It's just a pretend story to help you.
I'm wondering why it's not even fighting.
Do you understand now? Do you understand now?
I'm still lost, but I'm just...
Okay, you and I can play real quick. Ready?
I don't want to oxidize you.
So, how would somebody take this electron with a gun? They just hold up a gun and I throw it to them?
No. Wait, so she's giving it back?
So, if you want to oxidize somebody, that means you're taking electrons from them.
So the magnets...
Yeah, I mean, because a gun would not... You don't hold out a gun and then get a bullet come into the gun, right? That doesn't make sense. So you need like a magnet or something, right?
Yeah.
Okay,
This has gone too far.
it has. You're right.
We've all confused ourselves.
Okay. All right. So then, we need to have the ability to look at a reaction and say, hey, that is an oxidation or a redox reaction. A redox reaction. So let me explain again why we call them redox reactions. It's not appropriate to say an oxidation reaction. It's not appropriate to say a reduction reaction. Because if something's being reduced in a reaction, then something must also be what? Oxidized. And if something's being oxidized, something else must be reduced. So you can either say it's an oxidation reduction reaction, you can say it's a reduction oxidation reaction, or you can say it's a redox reaction, a redox. That's a single word that we've conjuncted to say reduction and oxidation. Okay? All right, so you need to be able to look at a reaction and say, hey, that's a redox reaction. Want to practice? Your line is, hey, that's a redox reaction, right? So how can we tell it's a redox reaction? Because we look at the oxidation number. Now, we called them charges in the past, and for ionic compounds, the charge on the ionic compound, on the monatomic ion, is the oxidation number. So if we look here, the first rule in terms of identifying what the oxidation number is on elements is that any free element is always 0. So here's sodium, no charge on it, so its oxidation number is what? 0. Another rule is that any simple monatomic ion is equal to the charge on the ion. So sodium in this ionic compound has what kind of a charge? Has a +1. And so that is its oxidation state as well. All right? So for the chemical reactions we've been doing, essentially, the charge on the ion can also be referred to as the oxidation state or the oxidation number. So you can look at sodium and see how its oxidation number has changed, and that's how you'll know it's an oxidation or a redox reaction. How about chlorine? What's its oxidation state here? 0, free element all by itself. What's the oxidation state here? -1, right? Okay? So that's one way that we can identify a redox reaction. We look at the oxidation state of the elements before and after the reaction, and if they've changed, then it's a redox reaction. Okay? Another thing we can look at is fluorine. If fluorine is in the compound, it's always a -1. So that's good to know and will come in handy later on when you least expect it to. Group 1 metals are always +1. It's like lithium, sodium, potassium, rubidium, cesium. They're always +1, which isn't surprising because we know that the compounds that they form are ionic and they always have a +1 charge. Yeah?
I have a question. So earlier we wrote that on the board, you had Na plus Cl minus. So why is it 0 now?
When did I have that?
I don't know, but I wrote it down in my notes like that.
Oh, you just didn't put the, yeah, you didn't put.
I put plus and a minus on there?
No, nothing.
There's nothing on there? Well, I shouldn't have put a plus on here, that's for sure. I mean, we do want to make sure we recognize that this thing loses an electron and this thing gains that electron, but they shouldn't start with a charge, right?
Okay, so when they're on the left side, they don't have charges.
If they did, right, if this was just the combination of these two ions, then the charges aren't changing, right? And that would not be an example of a redox reaction, right? And then you would say what? Hey, that's not a redox reaction, right?
But equations do have charges on the left side sometimes.
Yes, that's right. Sometimes they do. And so, for example, if I go something like this, O, oxygen, plus Pb plus 2, going to PbO2, like that. So, Is this a redox reaction? We have to be able to know. What's the charge on the oxygen? There's no charge. It's elemental. It's by itself. Any element that's just by itself is 0. What's the charge on the oxygen over here? What kind of compound is that? What kind of compound is that? Molecular, ionic? It's ionic. How can we tell? Has a metal in it. Very good. What is the name of this compound? What? That's lead. Pb is lead. Yep. Good. Not lead dioxide.
Oh, it's something to, like a oxide?
It is lead oxide. But if I just say, hey, I bought you some lead oxide, you're going to say, what kind? That's right. What kind of lead oxide is this? Lead 2 oxide?
Yes.
Nope. Lead 4. 4 oxide. Lead 4. What does that 4 mean? There's 2 oxygen. Why do we call it lead 4 oxide? What does the 4 mean? It's the charge on the lead. The charge on the lead. How did I know that there was a +4 charge on this lead? Because there's 2 oxygens, and oxygens always have what? A -2. A -2. All right, so here are our 2 -2s, and apparently there must be a lead here with what kind of a charge? +4. So it started off as lead +2 and went to lead +4. Is that an oxidation a redox reaction? It is, because it changed. It changed, right? What was it, oxidized or was it reduced? How can you tell? It lost 2 more electrons. That's right. Was oxygen oxidized or reduced? What was its charge here? 0, and now it's -2. So each oxygen did what? Gain or lost electrons? Gained electrons. Yeah. That's right. So you can say your line. What's the line? Hey, this is a redox reaction. That's right. This is a redox reaction. This is a redox reaction. Right? So it is possible for lead to have a charge here. True? And still do some sort of chemistry to get oxidized. Okay. Let's go back to our rules. First of all, let's make sure we gather these 2 rules. Group 1 is always +1. Group 2 is always +2. No, nothing surprising there. Hydrogen is a +1 in its compounds. And oxygen is -2. Oxygen is -2. Those are, again, no big surprise. Here's another piece of information that's valuable. The sum of all the oxidation numbers adds up to the charge on the molecule or compound. Sum of all the oxidation numbers. So here's this one, NaCl. What's the oxidation number on Na? +1. What's that on chlorine? -1. What's the charge on this thing, this whole overall compound? What's its charge? It's right there. See it? It's 0. Right. There's no charge. And that makes sense because this is a plus and that's a minus. Okay? Here's a species, PO4 3-. What's the overall charge on this species? It's 3-. Based on our rules, what is the oxidation number of these oxygens? -2. Very good. So there's 4 of these -2s. 1, 2, 3, 4. Oops. Did you see what I did? So it's a total of -8 contributed by these oxygens. What's the charge on the phosphorus? No rule about phosphorus. However, there is this rule, right? The sum of the oxidation numbers has to equal the charge on the compound. What's the oxidation, or what's the charge on this species? -3. Oops, we're running out of space. Let me level this up. Whatever the charge on the phosphorus is, plus the charge from these oxygens equals minus 3. So what's the charge on the phosphorus? Plus 5. Very good. So that's how we identify the charge on things that don't have a rule associated with them. Right? All these rules will help us identify the oxidation number. We will.
Oh my gosh.
There's not a single rule that I've introduced to you that's new yet, though. The first rule is that if elements are by themselves, their charge is 0. Ta-da! If I draw that, you know that the number of protons and electrons is the same. Right? So that means there's 0, right? If it's if it's in an ionic compound, and now you know how to find here's a crazy ionic compound. See this one? What's the charge on this zinc?
It's going to be
What's the charge on the chloride ion?
-1.
-1. The charge on the zinc?
+2.
+2. All right? So those are the oxidation numbers, right? Does that make sense? If it's an ionic compound, the charge on the atoms are the oxidation numbers. Right?
Okay.
So we haven't learned anything new yet, right? And we said oxygen always has what kind of a charge? -2, right? So there's nothing new. We haven't learned anything new yet.
Oh, we're just calling it like this.
That's right. We're calling it the oxidation number. Well, it is the oxidation number. We're not calling it. Now, we're going to learn.
Know that much before.
That's right. That's right. So there isn't hardly, you haven't learned anything new other than that what you thought were charges now also can be referred to as oxidation numbers. This is another thing that is kind of new, not terribly new, but the sum of all the oxidation numbers adds up to the charge on the polyatomic ion. Here's another one. Group 7, which is chlorine, bromine, and iodine, are -1, have a -1 charge. Now, here's a special rule. If there's a conflict of rules, then the rule that is higher up gets precedence in that list of rules. So, let's do some practice. What's the name of this compound? Iron 3 oxide. Very good. This is iron 3 oxide. So the 3 means the oxidation number, or sorry, the charge on the iron. And because it's an ionic compound, it's also the oxidation number. So iron is a +3 and oxygen is a -2. We won. How about this one? What's the name of the compound? No number needed, right? Sodium carbonate. We know sodium is what kind of a charge on it? +1. So its oxidation number is a +1. The oxygen is what kind of a charge on it? -2. -2. So its oxidation number is -2. The only one we don't know here is the carbon. How are we going to figure it out? How are we going to figure out the carbon? Here's Na2CO3. What's the charge on this species? 0. No charge. So the oxidation number from the sodiums plus the oxidation number from the carbons plus the collective oxidation from those 3 oxygens has to equal what? 0. What contributions do the oxygens make? -6. We said each oxygen has an oxidation state of -2. Sodium? Not negative, but +2, right? Each sodium has a +1. +4. All right, the end. Carbon has a +4. Okay, so that's how we play the game. All right, we'll see you guys when? Monday. Monday, yeah.
Does this test, is it just someone just 45?
1 through 5.
1 through 5?
Oh, that's right. We're going to have a party right now. Oh, how exciting.
Do we need to know the solubility for this one?
Well, it's going to be on the back of the, you have to know how to use them from the back of your periodic table.